Take a look at just a little bit of stuff today. We'll kind of split this up over 2 days. So here's what the homework. I'm going to put up an assignment. I'll probably put up 2 assignments today, but one of them you won't be able to do hardly anything on. The first one, the 1 point, is it 2? Well, I don't know whichever one it is. The next one is going to be on properties of limits that we talked about yesterday. That one you can do. It's got a number of questions, but they're all conceptual. There's almost no math to do. It's just you got to kind of read it and think about the question. Just very conceptual. Should go pretty quick. The third assignment that I'm going to put up, you already have one, right? There's 2 new ones. First new one is pretty quick and conceptual. The second new one is going to be over the stuff that we're going to start today. So if you want to jump into it and start it, you can. This one will take a little bit longer because there's more analytical stuff, more algebra stuff to do, calculus stuff to do. Okay, so where we left off, right? We were saying we're arriving at some strategies here for how do we deal with limits, right? And we said when we try to evaluate limits directly, one of 3 things is going to happen. First 2 are quick. Either it's going to work, which is great. You get an answer and you're done. Direct substitution works, or direct evaluation, whatever you want to call it, works and you're done. Option 2, you plug it in and you get something like a number divided by 0. Okay, that means the limit doesn't exist. We will be able to say more precise things about that. We're going to do an assignment pretty soon on infinite limits, and we'll be a little more specific about that. We'll take some one-sided limits, and you'll have to tell me a little bit more about it. But for the most part, at least temporarily, that we just stop with does not exist. Okay. The third thing, this is the thing that requires more work. We get an indeterminate form when we try to evaluate the limit directly. Okay, so we get something like 0 over 0. And for now, I think it's just exclusively going to be 0 over 0. But later on in the course, we're going to learn a better way to deal with these, and we'll introduce some other indeterminate forms. The AP test really, I think, only does 2 of them, but I want you to know more than that, so we'll spend a little extra time on that one. We'll look at 3 or 4 different indeterminate forms, and there are some techniques that are much quicker and easier once we know calculus for dealing with this stuff. So I don't want to spend a ton of time on it because we're going to have better techniques later anyway, but you need to kind of know how to do this analytically, even without knowing calculus, without knowing how to do derivatives. I want you to be familiar with this. Okay, so moving on. So what about something like this? Let's look up at the top here just for a second. Is x squared over x equal to x? Thumbs up or down? Okay, I'm seeing some thumbs up and I'm seeing a thumb down. I'm seeing a couple thumbs down. And I'd say, yes and no. Technically, strictly speaking, it is not. In many, it's very similar, and oftentimes we can reduce x squared over x to equal the function x, but they're not the same. They're actually different functions. If I look at the function f of x equals x squared over x, you tell me right away, are there any restrictions to the domain? What values of x must we eliminate from the domain? 0, yeah. Okay, so for the blue function, we know that x cannot equal 0. And what happens when we graph that function? Well, it's going to look like this. It's going to look like a diagonal line with a slope of 1 going through the origin. It looks like the function y equals x. However, because x equals 0 is excluded from the domain, we get a hole in the function at x equals 0. Okay? Would that show up on a graphing calculator? No, not unless you look for it, right? It's there, but it's not obvious. You'd have to go in on Desmos and actually either drag the little point to x equals 0 or evaluate the function at 0 to show that it's not defined there. So it's not obvious. Okay, so what happens if we simplify this? It's very easy to simplify this. X squared over x by our rules of exponents is equal to x. Okay, if we graph the function, new function, g of x equals x, here's what we get. We get the red line, which has no restrictions, right? So the red line is different. It's almost the same. The red line is exactly the same as the previous blue line at every point except one, except at x equals 0. When we simplify this and essentially cancel the x on the bottom, that's a way to think about this, right? Algebraically, what have we done here? We've just written f of x as x times x over x, and we've canceled one of those. We've canceled a factor. When we cancel that factor, that x on the bottom, we eliminate the exclusion to our domain, and that is effectively filling in the hole. So get used to that idea. When you simplify a rational function by canceling like factors, you're filling in a hole in the function. Okay, what's the value of that? How does that help us when we're trying to take a limit? If we want to take the limit of this function as x approaches 0, how does that help? Could we evaluate the blue function at 0? No, we couldn't, right? What's going to happen if we do? If we try to take the limit of the blue function, look what happens. The limit of f of x as x approaches 0 is 0 over 0, indeterminate, right? So that means more work. Okay, but what happens if we try to evaluate the red function? The limit of g of x as x approaches 0 is what? 0. Yeah, right? The limit of g of x equals x as x approaches 0 is just 0. So you see the point of that, right? Canceling those like factors gives us a new function that fills in the hole, which just happens to have the same limit as the original blue function. But it's easier to take the limit of the red function because the ant can step there, right? So we can answer the question, where does the ant anticipate stepping on the red function, by actually finding the value of the function, because he's going to step where he thinks he steps on the red function, but not the blue function, right? With the blue function, he anticipates stepping there, but he falls through a hole instead. He's no place to stand. Okay, make sense? Okay? All right. Okay. So what can we say about this? Here's kind of my way of describing this. Here's how the terminology I like to use. By canceling the offending factors. What do I mean by the offending factors? The factors that are causing the indeterminacy, that are causing us to have that 0 over 0 result when we plug in a value, right? By canceling those offending factors of the blue function f of x, the factors with zeros at x equals 0, you fill in the hole and generate a new function g of x whose limit you can easily find using direct substitution. That's our technique. This function shares the same limit as the original function, the one with the hole, as x approaches 0. So you've also found the limit of f of x, the original blue function. That's the whole point. Okay? Give me thumbs on that. Does that make sense? Okay? All right, and then here's some more stuff for your notes. Just kind of restating that. Okay. The limit of f of x as x approaches 0 is equal to the limit of g of x as x approaches 0, but it's just easy to evaluate the red function, g of x. Okay. So we use terminology. Essentially what we've done is we found a new function that agrees with the original function at all but one point. That's how we define that, or describe that in calculus. Okay? All right, and I'll promise you I'll get all this stuff up there, so it's all on Google Classroom. All these notes will be up there today. So what about one like this? What if we've got a slightly different situation now? We've got f of x, which is a piecewise function. So let's remind ourselves how that works, right? A piecewise function, the notation for that, we have f of x equals, and then we have an open script bracket, which is just going to give us a discrete row for each piece of the function. So in this case, there are two pieces to the function. There's the piece that corresponds to this polynomial, this quadratic polynomial, and that's defined every place other than x equals 1. So for all x values other than 1, That's the nature of the function. The other piece tells us that f of x is equal to 1 when x is exactly equal to 1. Okay, so the ant, for all values other than 1, the ant is walking along this parabola, but as soon as he steps on x equals 1, he's beamed down to that 1 point where he stands just for that 1 instant, and then he's back on the parabola again. Okay, give me thumbs. That'll make sense? Okay, so if our goal is to take the limit of f of x as x approaches 1, what are you going to do? Now, we don't want to rely on the graph. We want to be able to do this without looking at a graph too. That's right. We've entered the analytical phase of taking limits now, where we're not relying on graphs. Yes, Aiden. You could factor it, but it's not really going to buy you anything. You don't need to factor it. Plug in numbers. Okay, so if we plug in numbers, if I try to evaluate, you're moving in the right direction. If I evaluate f of 1, what's the answer? It's 1. Does that mean that's the value of the limit? Not quite. So what can you do here to find the limit? Very similar to what we did last time. Okay. Say it again. Yeah, fill in the hole. What we want to try to do is we want to find a new function that agrees with the old function everywhere except at that 1 point that we're interested in, right? The problem with f of x is when I step on x equals 1, I'm no longer on the parabola, right? So what do we do instead? Well, we're just going to trade f of x for some new function, call it g of x, which only includes the parabola, right? Everybody see that? By trading f of x for g of x, what's the only difference? Well, all we did was we essentially migrated that point up and filled in the hole, okay? How can we just do that? Well, because the reason we can do that is because the limits of these two functions are identical as x approaches 1. Everybody agree? Doesn't the ant anticipate stepping right there when he steps on x equals 1? From the graph, we can see that that value is 3, but again, we don't want to rely on the graph, right? Because what if the graph didn't happen to fall in a nice integer place? How would you know what decimal that is? You couldn't tell from a graph, right? Okay, so then our strategy was we're going to ignore that point and instead take just the parabola with no holes in it. And in order to find out where the ant anticipates stepping on f of x, we'll see where he actually steps on g of x because they're the same value. Give me thumbs. Does that make sense? Okay, so we can make the statement then, because the limit of f of x as x approaches 1, because that happens to be equal to the limit of g of x, that's g of x, right? The limit of g of x as x approaches 1, it's equal to the limit of x squared plus x plus 1 as x approaches 1. That's an easy limit to take using direct evaluation. What do we get if I plug 1 in? Yeah, 1 squared plus 1 is 3. Okay? See the strategy? Clever, clever. Okay, and then here's just some text that summarizes, what we just did, okay, for your notes, if you want to look back at this. All right. Questions so far? Okay. What about one like this? What do you think we're going to do there? Almost the same problem. It looks so similar, right? This time f of x is a little bit different though. It's not a piecewise function. It's a parabola. It looks like the same parabola we dealt with last time. Are there any restrictions to the domain of f of x? 1, yeah, right? So for f of x, x cannot equal 1. And look, we've got a hole in the function. So how are we going to fill in the hole this time and use a different, easier function that's identical to f of x but fills in the hole to take the limit? That's it, right? We're just going to factor the numerator, and if we do that, that's just a difference of cubes, right? X cubed minus 1 cubed, right? So a cubed minus b cubed is just a minus b times a squared plus ab plus b squared, right? You might be a little rusty on those things, but you're going to do more algebra this year than you've done by far in your entire high school career. So you'll be very good at algebra by the end of the year, I promise you. So we factor the top, we factor the bottom, and look what happens. The factors x minus 1 cancel. Does that fix our problem? It does, right? Because now as x approaches, when those cancel, we're left with a function that we can evaluate directly at 1. Okay? Did we luck out? What if it does? I mean, is there a chance it won't work that way? If I've got a rational function like we started with, and I'm taking a limit that gives me 0 over 0, is there a chance that maybe I won't be able to factor the top and cancel factors? Kind of seems like that could potentially happen, right? It cannot, right? It can't happen. It's always going to factor and they're always going to cancel. How do we know that? Because that's the only way I could get 0 over 0 is if x equals 1 is a 0 of the top and a 0 of the bottom, right? Think back to Algebra 2. We can make an important statement here about the connection between zeros and factors. It's the factor theorem. If x equals a is a 0 of f of x, then what is a factor? Guaranteed. If x minus a is a 0, then what's the factor we build from that? Remember? Well, you can kind of figure it out. Which factor would have a 0 at x equals a? What do you think? A linear factor, so it's going to be x plus or minus something. X plus 0? What do you think? Yeah, it's x minus a. Right? Is that ringing a bell? Okay. And you can get there algebraically in one step, really, because this is x minus a is a factor of f of x. Well, how would I find the 0 of a factor? Think about the steps you would have gone through to find the 0 of a factor. You would just set it equal to 0 and solve, right? X minus a equals 0. If I solve for x, what do I get? X equals a, right? So they go together, don't they? Right? See how this stuff all kind of, isn't it great how it all comes together when you get to calculus? Everything you learn, all of a sudden it just converges. Okay? Make sense? So now do you see why I told you, and it's the honest truth, that if we end up with a rational function whose limit is indeterminate of the form 0 over 0, the only way that can happen is when there are zeros of the top and the bottom at that value, which means that there are factors, that the factors of that 0 exist in the numerator and the denominator. So they have to cancel. Every time it's going to work. It's not an accident. Okay? Which is nice. You can depend on that. Tell you what, before we do that one, why don't you guys try that one. Go to the board and evaluate that limit for me. That's a good shirt, Anson. I like that shirt. That's a good shirt. Okay, everybody knew what they were doing there. That's good. However, very few, if anybody, actually wrote down what they needed to write down. And that's what I want to tell you now. And you guys are guilty of what everybody does. I've done it 1,000 times and more than that probably in school. You're just trying to get an answer, and you got an answer. You know, you were just testing yourself to see if you understood what was going on, and you did. However, in math, you have to be very specific. Like when we do this on the test, and we'll do kind of a combination of online / paper and pencil tests in here because I want to be able to really see your work on certain things. Like a lot of the really mechanistic, just rules of derivatives, earlier stuff, a lot of it's just going to be online. But as we get into more involved, process-driven stuff in calculus, I'm going to want to see all the steps, and you're going to be graded on all the steps, not just the answer, right? And so this is what this needs to look like, so watch closely. We are trying to evaluate a limit of this stuff. That's the argument of the limit, right? We have to keep that limit notation until we actually get a numerical answer. So you have to write limit for every step. This would look like this. Here's where we start. This would equal the limit of, we're going to factor the top, it's the limit as x approaches -3, we're able to cancel those factors. So this is equal to the limit of x plus 8 as x approaches -3, which I can now evaluate directly, and that's equal to 5, and that's your answer. Okay, but you notice how I have to state that I'm taking a limit of some stuff until I actually evaluate the limit. And then I get a number for my answer. The limit is 5. See what I'm saying? Okay, a lot of people, like nobody wrote down limit there, for example. Okay. All right. Okay, what about one like this? Now the good news is there are 3.5 different types of limits that we're going to start with that are indeterminate, and the techniques are all strongly related. They're all essentially the same thing. This just requires a little more algebra to get there, but it's the same exact concept we just had. If I evaluate this directly, what do I get? What do I get on top? 0. What do I get on bottom? 0. It's indeterminate. So you can already predict what's going to happen. When all the dust settles after we've done a whole bunch of algebra up here, what's going to cancel? What's going to cancel? And you know when x is going to 0, that's causing factors in the top and bottom to go to 0, right? So the fact that you know that x is approaching 0, you don't have to know anything about this problem. If you know that it's indeterminate of the form 0 over 0, you can already predict that if x equals 0 is a 0, then x minus 0, which is just x, is the factor that's going to cancel. You already know that, right? If x were approaching 2, and this were an indeterminate form, what would the factor be that's guaranteed to eventually cancel on the top and the bottom? If x were approaching 2 and I had something up here that would look like 0 over 0, what's the factor that's going to cancel? X minus 2. If it were x approaches -9, what would be the factor that's eventually going to cancel on the top and the bottom? If x is approaching -9, it would be x plus 9, x minus -9. You already know, you already have an idea, and if you know what's going to happen, it's easier to get there, right? You already anticipate what's going to happen. Now we just have to make it happen. So what are my options? Well, what's one thing I could do here to eventually get to that point? What would you do if you had to start somewhere and make some stuff happen algebraically? I mean, somehow we've got to simplify the top until we get to the point where we can factor out an x and cancel it with the bottom. We know that's going to happen. How could we get there? So we're just kind of focusing on all this stuff, right? What are you going to do with that stuff? Looks like a difference of two fractions to me. What are you going to do? So you're, in other words, you're, it sounds like, say it again. 1 over x plus. Okay, so you're trying to split this first one? Yeah. Can we do that? Let's explore that concept for a second. Can we do that? Is 1 over a plus b equal to 1 over a plus 1 over b? There's no easy way to do that. We can't split that. If the denominator is a plus b, we can't split a denominator, right? And use numbers to prove it to yourself. 1 over 2 plus 5. Is that equal to 1 over 2 plus 1 over 5? It's not, is it? Right? 1/7 is not going to be the same thing as 0.7, right? 7/10. So you can't do that. Now, numerators I could split, right? I can split numerators. I can either push denominators together into a common denominator and combine the numerators all into one, or I can split the fractions. That's okay to do. So this doesn't work, but this does. A plus b over c, I could easily make a plus c plus b over c, right? Everybody get that? C is just a common denominator, isn't it? Okay. So back to the drawing board. I can't do that. What could I do in the top, though? Okay, sounds like maybe you're getting a common denominator. Yeah, I could get a common denominator and combine the fractions, couldn't I? Right? So what would I multiply the first fraction by? 10 over 10, right? Okay. So I could multiply the first one by 10 over 10, second fraction by what? X plus 10 over x plus 10, right? I've got to have a product of common factors in the bottom. Agreed? Okay, what's that going to give me if I do that? So I'm going to get the limit of all the actions in the top, then I'm going to get 10 over 10 times the quantity x plus 10 minus x plus 10 over 10 times the quantity x plus 10. Right? Everybody good with that? Those are common denominators. I could push those together, and that whole thing's just over x. So I could push everything up there together into one big fraction and get the limit of 10 minus the quantity x plus 10 over 10 times the quantity x plus 10. That's my numerator, right? All divided by x as x approaches 0. And from there, it's just all going to kind of self-clean. Everything's going to be fine. We know it has to work, right? So if I distribute the negative on top, I'm going to get 10 minus x minus 10. Isn't that just negative x is what's left in my numerator? Right? Over 10 times x plus 10, all divided by x, which is the same as x over 1. And now look what I've got. Complex fraction. Big fraction on the top, big fraction on the bottom. Just flip and multiply by the bottom, right? Good. So we get the limit of negative x over 10 times x plus 10 times 1 over x. And we'll talk more about this on Tuesday. How about? Okay? All right. Have a great long weekend. Enjoy.